On October 23, 2018, thousands of football fans made their way into a Rome subway station. At around 7 p.m., a massive crowd packed tightly onto the long descending escalator. Everything seemed normal until the stairs beneath them suddenly gave way. The stairs began to plummet. Riders were flung forward, sweeping others into a crushing pileup at the bottom landing. The heavy metal steps twisted and buckled under the pressure, leaving 24 people injured. This type of failure goes against every engineering standard for modern escalators. These machines are built with massive tolerances. The step chain alone is rated for over 1.5 tons of weight. To prevent a runaway, they are equipped with 3 distinct, independent lines of mechanical defense. For all 3 systems to fail simultaneously is statistically improbable. In the aftermath, Rome's transit authorities sealed off the station, and investigators began dismantling the wreck piece by piece, suspecting that the cause wasn't just a mechanical fluke, but something much more deliberate. So how does a machine designed with triple redundant, heavy-duty failsafes turn into a runaway trap? To understand that, we have to look at the mechanical logic of the moving staircase. The escalator actually began as a theme park attraction. In 1896, over 75,000 people rode this continuous elevator during its 2-week stay at Coney Island's Old Iron Pier. It didn't have any stairs. It was essentially a flat conveyor belt made of wood and metal, set at a steep 25-degree angle. Because that is the absolute limit of how far a human ankle can flex, riders found the experience incredibly unnerving. The obvious fix was to replace the belt with a loop of flat stairs. But early revolving stairs created a new hazard. As the steps reached the top or bottom, they tilted forward, making it nearly impossible to step off without tripping. George Wheeler solved this by attaching each step to a pivot, guided by 2 wheel sets on separate tracks. At the landing, the tracks separate, keeping the step horizontal before it tucks away and flips for the return journey. This looping mechanism was the breakout star of the 1900 Paris Exposition. It was an immediate success, and it remains the mechanical foundation for every modern escalator in use today. But while Wheeler solved the geometry of the staircase, the continuous loop introduced dangerous new pinch points where the moving steps met the stationary floor. Early escalators used smooth, flat wooden steps that slid under a board at the landing. This created a tight gap that easily trapped shoelaces, long skirts, and toes. Today, steps are deeply grooved so they can interlock with a stationary comb plate at the landings. These teeth effectively lift objects up and out of the gap, allowing riders to step off forward with much less risk. Engineers also had to account for the handrail. It's driven by a separate internal friction wheel, but because friction inevitably wears that wheel down, its circumference shrinks over time. To prevent the handrail from lagging behind the stairs, factories calibrate the wheel to move the handrail exactly 2% faster than the steps. This ensures that even as the parts wear down, the handrail stays in sync with the rider. These machines are packed with hidden mechanical tolerances, specifically designed to protect humans from natural wear and tear. The most robust safeguard of all is the drive motor itself. Modern escalators use AC induction motors, which naturally regulate their own speed. As passengers push the downward stairs faster, the motor's magnetic field resists the spin, creating an automatic braking force. This resistance also turns the escalator into a generator, converting mechanical energy into electricity that feeds back into the building's grid. This regenerative braking provides an enormous safety margin. The physics of the induction motor keep the descent speed strictly regulated, even when fully loaded. Even with those margins, every motor has a physical limit. In Rome, as football fans crowded onto the stairs, the combined weight reached a tipping point where the motor could no longer hold the load, and the drive system began to slip. The machine sensed the runaway and triggered the first failsafe, the main brake. But when investigators tested it later, they found it was severely degraded, providing only 37% of the required stopping power. Finally, the ultimate failsafe was triggered. An auxiliary brake deployed steel wedges directly into the drive shaft to lock it in place, but it only engaged at 50% capacity, failing to halt the plummet. A failure of this scale should have triggered digital alarms months earlier, but the system had remained silent, suggesting the failures weren't just overlooked, but hidden. Inside the machine, investigators found something shocking. The auxiliary emergency brake had been intentionally disabled. Someone had wrapped the heavy industrial wedges in plastic zip ties, rendering them useless. The digital error logs were also empty. They had been deliberately reprogrammed and turned off, so the machine could experience critical malfunctions without leaving a trace. The investigators uncovered a pattern of fraud. Maintenance contractors and transit authorities had been sabotaging their own safety systems simply to avoid the inconvenience of shutting down the escalators for proper repairs. A wiretap later caught a transit manager callously dismissing the risk. He suggested that with hundreds of escalators in the network, it was a simple matter of percentages that 3 or 4 of them would eventually drop. Over the last century, the escalator has evolved through meticulous engineering into a global utility that moves billions of people a year with incredible reliability. But as the investigations in Rome proved, even the most robust system is only as safe as the people trusted to maintain it.